Right now, as you're watching this video, there's a world 124 light-years away that has captured the imagination of scientists and space enthusiasts worldwide. A planet that made headlines as potentially being our cosmic neighbour's most promising candidate for life. A world that some researchers claimed had a staggering 99% chance of harbouring living organisms. But what if everything we thought we knew about this distant planet was built on a foundation of wishful thinking and misinterpreted data? Tonight we're diving deep into the controversial story of K218b, and by the time we're finished, you'll understand why some of the world's most respected astronomers are now questioning whether this so-called super-Earth might actually be one of the most hostile environments imaginable. Before we embark on this cosmic detective story together, I'd love to know where you're tuning in from tonight and what keeps you fascinated by the search for life beyond our solar system. And I'd be grateful if you gave this video a like and perhaps subscribe to join our community of cosmic truth seekers. Get ready. The journey begins now. This is the story of how humanity's desperate search for a second Earth led us to embrace evidence that may have been too good to be true. And by the time we're done tonight, you'll see how the same scientific tools that promise to reveal alien worlds might also be deceiving us about what's really out there in the cosmic darkness. Picture this scene from 2015. NASA's Kepler Space Telescope, humanity's most prolific planet hunter, is conducting its systematic survey of distant stars when it detects something extraordinary. A world orbiting a red dwarf star in the constellation Leo, positioned in what astronomers call the habitable zone. That sweet spot where liquid water could theoretically exist on a planet's surface. This wasn't just another exoplanet discovery. This was K218b, and it would soon become the poster child for our cosmic search for life. The numbers seemed almost too perfect to believe. K218b sits exactly 124 light-years from Earth, close enough for our most advanced telescopes to study in detail, yet far enough to represent a truly alien world. It orbits its host star every 33 days, receiving roughly the same amount of stellar radiation that Earth gets from our Sun. The planet itself is about 2.6 times the radius of Earth and weighs in at nearly 9 times our planet's mass. These measurements placed it squarely in a category that astronomers call sub-Neptunes, worlds larger than Earth but smaller than Neptune that don't exist anywhere in our own solar system. But here's what made K218b truly special in the eyes of researchers. Unlike the scorching hot, Jupiter-sized worlds that had dominated exoplanet discoveries up to that point, this planet seemed to offer something unprecedented, a world that might actually be cool enough, stable enough, and positioned just right to harbour the liquid water that life as we know it requires. The excitement was immediate and intense. Within months of its discovery, K218b was being hailed in scientific papers and news headlines as potentially the most Earth-like world ever found. Researchers began conducting detailed atmospheric studies using the Hubble Space Telescope, searching for the chemical signatures that might reveal whether this distant world truly was the second Earth that humanity had been searching for since we first looked up at the stars and wondered if we were alone. What they found seemed to confirm their wildest hopes. In 2019, scientists announced that they had detected water vapour in K218b's atmosphere, not just traces, but significant amounts that suggested the planet might indeed harbour vast oceans beneath its alien skies. The discovery made international headlines. Here was direct evidence that a potentially habitable world existed within reach of our telescopes, a cosmic laboratory where we might finally answer the age-old question of whether life exists beyond Earth. The scientific community's response was electric. Papers began emerging that painted increasingly optimistic pictures of K218b's potential for habitability. Some researchers went so far as to suggest that the planet represented our best current candidate for finding extraterrestrial life, with conditions that might not just allow life to exist, but to thrive in ways that could be detectable from our distant vantage point. This is where our story takes a dramatic turn toward the revolutionary capabilities of the James Webb Space Telescope. When JWST turned its unprecedented infrared vision toward K218b, astronomers expected to find confirmation of what Hubble had suggested. Instead, they discovered something far more complex and controversial. The Webb telescope revealed that K218b's atmosphere contains not just water vapor, but a cocktail of molecules that painted a picture unlike anything in our solar system. Methane and carbon dioxide, each making up about 1% of the planet's atmosphere. A hydrogen-dominated envelope that suggests this world is fundamentally different from the rocky planets we're familiar with. And most intriguingly, tentative detections of more exotic molecules that some scientists claimed could only be produced by living organisms. The data seemed almost too good to be true. Here was a world that appeared to have all the ingredients for life: liquid water, a stable orbit in the habitable zone, and atmospheric chemistry that some researchers interpreted as potential biosignatures. The excitement reached fever pitch when some scientists began claiming that K218b might have a 99% chance of harboring life, based on atmospheric models that suggested biological processes were the most likely explanation for the chemical signatures they were observing. But science has a way of humbling our greatest hopes, and K218b was about to become a cautionary tale about the dangers of cosmic wishful thinking. As more scientists began examining the Webb telescope data, cracks started appearing in the optimistic narrative that had captured global attention. The first problem was fundamental. K218b might be located in what we call the habitable zone, but that doesn't necessarily mean it's habitable. The planet's size and mass suggested something troubling. At 2.6 times Earth's radius and 9 times its mass, K218b possesses a gravitational field so intense that it can hold onto a massive hydrogen atmosphere, the kind of thick gaseous envelope that characterizes the ice giants in our own solar system. This revelation forced astronomers to confront an uncomfortable possibility. What if K218b wasn't the ocean world they had imagined, but something far more alien and hostile? What if the water vapor signatures they had detected weren't evidence of vast oceans, but traces of moisture trapped in a crushing hydrogen atmosphere that would be utterly lethal to any Earth-like life? The mathematics of K218b's atmospheric structure paint a disturbing picture. If this world does possess the hydrogen-rich envelope that its size and mass suggest, then the pressures and temperatures at any potential surface would be beyond anything that life as we know it could survive. We're talking about atmospheric pressures thousands of times greater than what exists at Earth's surface, combined with temperatures that could reach thousands of degrees Fahrenheit. Under such conditions, the complex molecular structures that enable life would be torn apart long before they could organize into anything resembling biological systems. Even more troubling is the possibility that K218b doesn't have a solid surface at all. The planet's density and composition suggest it might be what astronomers call a mini Neptune, a world where any rocky core is buried beneath layers of high-pressure ice and gas so deep that the boundary between atmosphere and interior becomes meaningless. If this interpretation is correct, then K218b represents not a potentially habitable world, but a fundamentally alien type of planet that has no analogue in our solar system and no possibility of supporting life as we understand it. The debate over K218b's true nature reveals a deeper problem in exoplanet science: the challenge of interpreting atmospheric data from worlds so distant that we can only observe them indirectly. When astronomers detect molecules like water vapor and methane in an exoplanet's atmosphere, they're making inferences based on how starlight filters through that atmosphere during the brief moments when the planet passes in front of its host star. This technique, called transmission spectroscopy, is incredibly sophisticated, but it's also prone to false positives and misinterpretations. Consider what happened when scientists began looking more closely at the methane detections in K218b's atmosphere. On Earth, methane is often produced by biological processes, leading some researchers to interpret its presence as a potential biosignature. But in the context of a hydrogen-rich atmosphere, like the one K218b likely possesses, methane can be produced through entirely non-biological chemical processes. The same atmospheric conditions that initially seemed to suggest the possibility of life might actually be evidence of chemistry so exotic and extreme that life would be impossible. This is where the story of K218b becomes a lesson in the psychology of scientific discovery. When we're searching for something as profound as extraterrestrial life, there's an almost irresistible temptation to interpret ambiguous data in the most optimistic possible light. The molecules detected in K218b's atmosphere could potentially be produced by biological processes, and in our eagerness to find cosmic companions, some researchers may have rushed to embrace the most exciting interpretation without fully considering the alternatives. The controversy deepened when scientists began reporting the detection of even more exotic molecules in K218b's atmosphere, including compounds like dimethyl sulfide that on Earth are produced almost exclusively by living organisms. These claims generated enormous excitement in the astrobiology community, with some researchers suggesting that we might be seeing the first genuine biosignatures ever detected on an exoplanet. But as we'll explore in detail, these detections have proven to be far more controversial and uncertain than the initial headline suggested. The case of K218b illustrates a fundamental challenge in the search for habitable worlds: the difference between what we hope to find and what the data actually tells us. When we compare K218b to genuinely Earth-like worlds, the differences become stark and troubling. Earth maintains its habitable conditions through a delicate balance of factors: a thin atmosphere dominated by nitrogen and oxygen, moderate surface pressures that allow liquid water to exist, and a magnetic field that protects complex molecules from destructive radiation. K218b possesses none of these characteristics. Its massive hydrogen atmosphere would create greenhouse effects so intense that any water would exist only as superheated vapor. Its lack of a solid surface means there's no stable platform where complex chemistry could develop and persist. Its proximity to a red dwarf star subjects it to radiation environments that would be hostile to the kinds of organic molecules that enable life on Earth. Yet the allure of K218b as a potentially habitable world has proven remarkably persistent, even as evidence has mounted against its suitability for life. This persistence reveals something profound about human nature and our relationship with the cosmos. We are a species that evolved on a single remarkable world, and our entire understanding of habitability is shaped by the specific conditions that made our own existence possible. When we encounter worlds that seem to share some of Earth's characteristics, we may be predisposed to see similarities rather than differences, hope rather than harsh reality. The scientific debate over K218b has become increasingly heated as different research teams have reached fundamentally different conclusions about the same data. Some continue to argue that the planet represents our best current candidate for finding extraterrestrial life, pointing to atmospheric models that suggest biological processes could explain the observed chemical signatures. Others have become increasingly skeptical, arguing that the data is better explained by exotic atmospheric chemistry that has nothing to do with life. This disagreement isn't just academic. It represents a crucial test of our ability to objectively interpret data about distant worlds and resist the temptation to see what we want to see rather than what's actually there. The stakes couldn't be higher. If we misinterpret the signals from K218b, we might be setting ourselves up for disappointment on a cosmic scale, while potentially missing the truly habitable worlds that are waiting to be discovered. As we continue our investigation of K218b's dark truth, we'll explore how cutting-edge telescope technology is revealing the reality behind the headlines, and why this distant world might teach us more about the rarity of truly habitable planets than about the abundance of life in the universe. The story of K218b is far from over, and its implications for our search for cosmic companions are more profound and troubling than anyone initially realized. The turning point came when astronomers began to scrutinize the very foundation of K218b's habitability claims. The more they looked, the more troubling the picture became. The planet's classification as a sub-Neptune wasn't just an academic detail. It was a fundamental clue about its true nature that had been overlooked in the initial excitement. You see, sub-Neptunes don't exist in our solar system for a very good reason. The gap between rocky planets like Earth and Mars and gas giants like Neptune and Uranus isn't accidental. It represents a crucial threshold in planetary physics, a boundary between worlds that can maintain solid surfaces and those that become dominated by thick, crushing atmospheres. K218b sits squarely on the wrong side of that boundary. When scientists began modelling what K218b's interior structure might actually look like, the results were sobering. The planet's mass and radius suggested a world where any rocky core would be buried beneath layers of high-pressure ice and gas extending for thousands of kilometres. We're not talking about a world with a thick atmosphere sitting on top of solid ground. We're talking about a planet where the very concept of a surface becomes meaningless, where pressures increase so dramatically with depth that rock itself begins to behave like liquid. This revelation forced researchers to confront an uncomfortable question. Had they been so eager to find a habitable world that they'd ignored the most basic physics of planetary formation? The same measurements that initially seemed to place K218b in the habitable zone were actually telling a very different story about a world that might be fundamentally hostile to life as we know it. The controversy deepened when multiple research teams began reanalyzing the James Webb Space Telescope data with fresh eyes and more sophisticated models. What they discovered was a masterclass in how easy it is to misinterpret signals from distant worlds. The methane detections that had initially seemed so promising, potentially indicating biological processes, could be explained just as easily by exotic atmospheric chemistry occurring in the crushing depths of a hydrogen-rich envelope. Think about what this means for a moment. In a hydrogen-dominated atmosphere, like K218b likely possesses, chemical reactions can occur that simply don't happen anywhere on Earth. Thermochemical processes in the deep atmosphere can produce methane, carbon dioxide, and even water vapor through purely geological mechanisms. Then transport these molecules upward to the observable regions where our telescopes detect them. No life required, no biology necessary, just the alien chemistry of a world so different from Earth that our terrestrial intuitions lead us astray. But the most controversial chapter in K218b's story was yet to come. In early 2023, a team of researchers led by Niku Madhusudan from Cambridge University announced something that sent shockwaves through the astrobiology community. They claimed to have detected dimethyl sulfide, or DMS, in K218b's atmosphere at concentrations 20 times higher than what we observe on Earth. This wasn't just another atmospheric molecule. On our planet, DMS is produced almost exclusively by marine microorganisms, making it one of the most promising potential biosignatures we could hope to find on an exoplanet. The implications were staggering. If confirmed, this detection would represent the first genuine biosignature ever identified on a world beyond our solar system. The research team calculated that maintaining such high concentrations of DMS in K218b's atmosphere would require biological production on a scale that dwarfed Earth's entire marine ecosystem. They were claiming, in effect, that K218b might harbour life forms so abundant and active that they could alter the chemistry of an entire planetary atmosphere. The scientific community's reaction was swift and divided. Some researchers embraced the findings as potential evidence for the discovery of the century. Others immediately raised red flags about the methodology and interpretation. The statistical significance of the detection was marginal, hovering at what scientists call a 3 sigma confidence level. In simple terms, there was still a 0.3% chance that the signal was nothing more than cosmic noise masquerading as a molecular signature. But the real controversy erupted when researchers began questioning whether DMS could only be produced by biological processes. A series of discoveries in 2024 and 2025 revealed that this assumption, fundamental to the biosignature claim, might be completely wrong. Scientists detected DMS on a cold, lifeless comet, demonstrating that the molecule could form through entirely non-biological processes in space environments. Laboratory experiments showed that under the right conditions, DMS could be synthesized abiotically, without any involvement of living organisms whatsoever. These revelations struck at the heart of the biosignature claim surrounding K218b. If DMS could be produced by non-biological processes, then its detection in the planet's atmosphere proved nothing about the presence of life. The molecule that had seemed like such compelling evidence for extraterrestrial biology might actually be telling us about exotic chemistry occurring in environments so extreme that life would be impossible. The backlash was immediate and intense. Jake Taylor from Oxford University conducted an independent reanalysis of the same Webb telescope data using different statistical methods. His conclusion was devastating. The data was consistent with a flat line, meaning there was no clear evidence for any of the exotic molecules that had generated so much excitement. Other research groups reached similar conclusions, suggesting that the DMS signal existed more in the hopes of the researchers than in the actual observations. NASA assembled its own team to review the controversial claims, incorporating multiple independent analyses of the Webb telescope data. Their findings were diplomatically worded, but scientifically clear. No conclusive evidence for DMS could be found. Despite the previously reported tentative detection, the agency confirmed that K218b possessed a water-rich atmosphere and contained methane and carbon dioxide, but the exotic biosignature molecules remained below the threshold required for scientific acceptance. This pattern of initial excitement, followed by sober reassessment, has become disturbingly familiar in exoplanet science. The 2020 announcement of phosphine in Venus's atmosphere, initially hailed as potential evidence for aerial microbes, was later challenged when researchers demonstrated that the signal could be explained by non-biological processes. The 1996 claim of fossilized bacteria in a Martian meteorite was similarly undermined when the supposed biological structures were shown to form through purely chemical means. K218b was following the same trajectory, transforming from humanity's best hope for finding extraterrestrial life into a cautionary tale about the dangers of cosmic wishful thinking. But the story reveals something even more troubling about our current approach to searching for habitable worlds. The fundamental problem isn't just that we misinterpreted the data from K218b, it's that we may have been asking the wrong questions entirely. The planet's location in the so-called habitable zone, that region around a star where liquid water could theoretically exist, had become a kind of cosmic holy grail, leading researchers to focus on worlds that might not be habitable at all. Recent research has revealed that K218b's position relative to its host star may actually preclude habitability entirely. The planet receives substantial, high-energy radiation that would be lethal to surface organisms. Numerical models suggest that its atmospheric properties restrict its possible reflectivity to values below the threshold required for maintaining liquid water on any surface. The greenhouse effect from its massive hydrogen atmosphere would likely create temperatures so extreme that any water would exist only as superheated vapor. Even more damning is the possibility that K218b represents what scientists now call a magma ocean world. Instead of the temperate oceanic paradise that early headlines suggested, the planet might be a hellscape where molten rock churns beneath a crushing atmospheric envelope. Some researchers have concluded that a magma ocean model actually fits the Webb telescope observations better than the water world hypothesis, suggesting that what appeared to be evidence for habitability might actually indicate conditions of unimaginable hostility. These revelations have forced astronomers to confront a deeply uncomfortable possibility that truly habitable worlds might be far rarer than we had hoped. The sub-Neptune planets that dominate exoplanet surveys, worlds like K218b that seem so promising, might represent a category of planets that are fundamentally incompatible with life as we know it. Their large sizes and massive atmospheres create conditions so extreme that the complex molecular chemistry required for biology simply cannot occur. This realization has profound implications for our cosmic search for companions. If sub-Neptunes are uninhabitable, then we need to focus our attention on smaller, more Earth-like worlds that are much harder to detect and study with current technology. The James Webb Space Telescope, powerful as it is, struggles to analyze the atmospheres of truly Earth-sized planets. We may need to wait for the next generation of space-based observatories, missions like the proposed Habitable Worlds Observatory planned for the 2040s, before we can definitively characterize potentially habitable worlds. But K218b's story raises even more fundamental questions about the nature of habitability itself. Our entire search for extraterrestrial life is based on the assumption that life requires conditions similar to those on Earth: liquid water, moderate temperatures, and stable chemical environments. What if this assumption is limiting our cosmic vision? What if life can adapt to environments so exotic that we wouldn't even recognize them as potentially habitable? Some researchers have begun exploring the possibility that life might exist in hydrogen-rich atmospheres like the one K218b possesses. Perhaps organisms could evolve to thrive in high-pressure environments using chemical pathways that don't exist on Earth. Maybe the crushing atmospheric conditions we consider lethal could actually provide energy sources for alien biochemistry we've never imagined. These speculations push the boundaries of astrobiology into truly alien territory. Instead of searching for worlds that look like Earth, we might need to expand our definition of habitability to include environments that seem utterly hostile from our terrestrial perspective. This approach could open up vast new categories of potentially habitable worlds, but it also makes the search for life exponentially more difficult. How do you look for life forms that might operate according to principles you don't understand, in environments you've never encountered, using chemistry that doesn't exist on your home planet? The challenge becomes not just technical, but conceptual. We're trying to imagine forms of biology that evolution on Earth never explored, in worlds so alien that our very concepts of life and death might lose their meaning. The controversy surrounding K218b has also highlighted the psychological challenges facing researchers in the search for extraterrestrial life. When you're looking for something as profound as cosmic companions, there's an almost irresistible temptation to interpret ambiguous data optimistically. The possibility that we might not be alone in the universe is so compelling that it can unconsciously bias our analysis of the evidence. This bias isn't necessarily a flaw in the scientific process. It's a reflection of our deep human need to find meaning and connection in the cosmos, but it can lead us to embrace conclusions that aren't fully supported by the data, especially when those conclusions align with our hopes and expectations. The case of K218b suggests that we might need to develop new methodologies for evaluating potential biosignatures, approaches that are specifically designed to counteract our natural optimism about finding life. Some researchers have proposed that extraordinary claims about extraterrestrial life should be held to extraordinary standards of evidence. Instead of accepting tentative detections at the 3 sigma confidence level that's standard in astronomy, biosignature claims might require 5 sigma certainty, the same threshold used in particle physics for fundamental discoveries. This would mean that false positive rates would drop from 0.3% to 0.00006%, virtually eliminating the possibility of mistaking cosmic noise for biological signals. But even with more rigorous standards, the fundamental challenge of interpreting data from distant worlds remains formidable. We're trying to understand planetary environments based on incredibly limited information, brief glimpses of starlight filtered through alien atmospheres, chemical signatures that could have multiple explanations, physical measurements that require extensive theoretical modelling to interpret. The story of K218b illustrates just how easy it is to construct compelling narratives from fragmentary data, especially when those narratives align with our deepest hopes about the cosmos. The planets seem to check all the boxes for habitability: the right size, the right location, the right atmospheric chemistry. But as we've learned, checking boxes isn't enough. The universe is under no obligation to conform to our expectations or fulfill our desires for cosmic companionship. Perhaps the most valuable lesson from K218b isn't about this particular world, but about the nature of scientific discovery itself. The process of investigating this distant planet has revealed the limitations of our current technology, the biases in our interpretation of data, and the challenges of maintaining objectivity when studying phenomena that touch our deepest questions about existence and meaning. The debate over K218b continues, with different research teams reaching fundamentally different conclusions about the same observations. Some still maintain that the planet could harbour life, pointing to atmospheric models that suggest biological processes might explain some of the chemical signatures. Others have become increasingly convinced that K218b represents a fundamentally hostile environment where life, as we know it, could never survive. This ongoing disagreement isn't a failure of science, it's science working exactly as it should. When confronted with ambiguous data about phenomena at the limits of our technological capabilities, researchers are supposed to debate, challenge, and refine their interpretations. The controversy surrounding K218b is pushing astronomers to develop better models, more sophisticated analysis techniques, and clearer criteria for evaluating potential biosignatures. But while scientists continue their debates in academic journals and conference halls, the broader implications of K218b's story are already becoming clear. This distant world has taught us that the search for habitable planets is far more complex and challenging than we initially realized. The universe might be filled with worlds that seem potentially habitable from our distant perspective, but turn out to be utterly alien when examined in detail. This uncertainty isn't just academic, it's reshaping our entire approach to finding life beyond Earth. The case of K218b has become a watershed moment in astrobiology, forcing us to confront the possibility that our methods for identifying habitable worlds might be fundamentally flawed. Consider what happened when researchers began comparing K218b to other worlds in our cosmic neighbourhood. The contrasts are stark and revealing. Mars, despite being cold and dry today, shows clear evidence of ancient riverbeds, lake deposits, and mineral formations that could only have formed in the presence of liquid water. We can literally see the geological scars left by a more hospitable past, written in stone across the Martian landscape. The TRAPPIST-1 system, located about 40 light-years from Earth, offers 7 terrestrial-sized planets, 3 of which orbit within their star's habitable zone. These worlds are small enough that they almost certainly possess solid surfaces, and their proximity to each other creates a cosmic laboratory where we can study how planetary atmospheres evolve under slightly different conditions. Early observations suggest that some of these planets might indeed harbour the kind of thin, temperate atmospheres that could support liquid water. Even Kepler 452b, often called Earth's older cousin, presents a more compelling case for habitability than K218b. Despite being about 60% larger than Earth, this distant world orbits a sun-like star at a distance that would allow for moderate surface temperatures. Its size suggests it might be rocky rather than gas-dominated, and its 385-day orbital period indicates seasonal variations that could drive the kind of climate dynamics we associate with habitable environments. What makes K218b different and potentially problematic is precisely what made it seem so exciting initially. Its larger size allowed astronomers to detect atmospheric signatures more easily than they could with smaller, truly Earth-like worlds. But that same size is now revealing itself to be K218b's fatal flaw. The planet is simply too massive to maintain the kind of thin, stable atmosphere that complex life requires. The physics are unforgiving. When a planet reaches about 1.7 times Earth's radius, it crosses a crucial threshold where it can begin retaining significant amounts of hydrogen and helium from its formation period. K218b, at 2.6 times Earth's radius, sits well beyond this boundary in what scientists now call the radius gap, a region where planets become dominated by thick gaseous envelopes rather than maintaining rocky surfaces. This realization has profound implications for how we categorize potentially habitable worlds. The traditional approach of simply looking for planets in the habitable zone may be misleading us toward worlds that appear promising from a distance, but are actually utterly hostile up close. We might need to completely revise our search strategies, focusing on smaller planets that are much harder to detect, but more likely to possess the stable, temperate conditions that life requires. The debate over K218b has also revealed deep philosophical divisions within the scientific community about how we should approach the search for extraterrestrial life. One camp, led by researchers like those who initially championed the planet's habitability, argues for what we might call optimistic interpretation. They suggest that when we detect potentially biological signatures, we should seriously consider the possibility of life, even if alternative explanations exist. The opposing camp advocates for what they call extraordinary skepticism. These researchers argue that claims about extraterrestrial life are so profound that they require overwhelming evidence before acceptance. They point to the long history of false alarms in astrobiology, from the Martian meteorite controversy to the phosphine claims on Venus, as justification for extreme caution in interpreting potentially biological signals. This philosophical divide isn't just about K218b. It reflects a deeper tension about humanity's place in the cosmos and our psychological readiness to accept that we might not be alone. Are we so eager to find cosmic companions that we're seeing life where none exists? Or are we so afraid of being wrong that we're dismissing genuine evidence when it finally appears? The concept of Hycean worlds sits at the center of this debate. These hypothetical planets, with their hydrogen-rich atmospheres overlying vast liquid water oceans, represent either the next frontier in habitability research or a dangerous distraction from truly Earth-like worlds. K218b was supposed to be the prototype for this new category of potentially habitable planets, but its controversial nature has cast doubt on whether Hycean worlds can exist at all. Recent theoretical work suggests that most sub-Neptune planets, rather than hosting temperate oceans beneath hydrogen atmospheres, would experience runaway greenhouse effects that would boil away any liquid water. The hydrogen envelope that was supposed to create a protective blanket might actually function as a cosmic pressure cooker, creating conditions so extreme that even the most resilient forms of life would be instantly destroyed. But here's where the story takes another fascinating turn. Some researchers have begun exploring whether life might be possible in environments so alien that our Earth-based intuitions completely fail us. What if organisms could evolve to thrive in high-pressure hydrogen atmospheres? What if the crushing conditions we consider lethal could actually provide energy sources for exotic forms of biochemistry? These speculations push us into truly uncharted territory. We're talking about life forms that might use chemical pathways that don't exist on Earth, organisms that could harness the immense pressures and temperatures of hydrogen-rich atmospheres to drive metabolic processes we've never imagined. Such life would be so fundamentally different from terrestrial biology that we might not even recognize it as life if we encountered it. This possibility raises profound questions about our search methodologies. If life can adapt to environments as extreme as those potentially found on K218b, then our current approach of looking for Earth-like biosignatures might be hopelessly narrow. We could be surrounded by thriving alien biospheres that operate according to principles so different from our own that they remain completely invisible to our detection methods. The James Webb Space Telescope, powerful as it is, was designed to look for the kinds of molecular signatures that we associate with life on Earth: oxygen, ozone, water vapor, and organic compounds that form under temperate conditions. If alien life operates through hydrogen chemistry at extreme pressures and temperatures, Webb might be completely blind to its existence, no matter how abundant or active it might be. This technological limitation highlights one of the most challenging aspects of exoplanet science. We're trying to understand alien worlds using instruments and concepts developed on a single planet. Our entire framework for habitability is based on the specific conditions that enabled life to emerge and thrive on Earth. But what if Earth represents just one narrow pathway among countless possibilities for biological organization? The controversy surrounding K218b has also sparked intense debate about the statistical methods used to analyze exoplanet data. When astronomers detect molecular signatures in distant atmospheres, they're essentially trying to match observed patterns of starlight absorption to theoretical models of atmospheric composition. This process requires making numerous assumptions about temperature, pressure, chemical reactions, and atmospheric dynamics that may not hold true for worlds as exotic as K218b. The problem becomes even more complex when researchers attempt to distinguish between biological and non-biological explanations for observed molecular signatures. The same compounds that life produces on Earth can often be generated through purely chemical processes under the right conditions. Distinguishing between these possibilities requires not just detecting the molecules themselves, but understanding the broader atmospheric context in which they exist. This interpretive challenge is at the heart of the ongoing controversy over K218b's dimethyl sulfide detections. Even if the molecule is genuinely present in the planet's atmosphere, and that's still hotly debated, its existence doesn't necessarily imply biological activity. The discovery that DMS can be produced abiotically in space environments has fundamentally undermined the biosignature interpretation, but it hasn't resolved the broader questions about what the atmospheric chemistry of K218b actually tells us about the planet's nature. Future observations may help clarify these questions, but they're also likely to raise new ones. The James Webb Space Telescope is scheduled to conduct additional observations of K218b that could either strengthen or refute the claimed detections of exotic molecules. These follow-up studies will test whether the controversial signals are repeatable and consistent, or whether they represent instrumental artifacts or statistical flukes. But even definitive detections of specific molecules won't necessarily resolve the habitability debate. The fundamental question isn't whether K218b has an interesting atmospheric chemistry, it clearly does, but whether that chemistry is compatible with the existence of life as we understand it. This question may remain unanswered until we develop new theoretical frameworks for understanding how biology might operate under conditions radically different from those on Earth. The technological horizon offers some hope for clarification. The proposed Habitable Worlds Observatory, tentatively scheduled for launch in the 2040s, would be specifically designed to study Earth-sized planets in detail, potentially resolving questions about truly habitable worlds that current instruments can't address adequately. Ground-based telescopes, like the extremely large telescope currently under construction, will provide unprecedented resolution for studying exoplanet atmospheres. But these future instruments also raise the possibility that K218b's story might be repeated many times over. As our detection capabilities improve, we're likely to discover many more worlds that seem potentially habitable from a distance, but turn out to be hostile when examined in detail. The universe might be filled with planets that tantalize us with the possibility of life, while remaining fundamentally unsuitable for biology as we know it. This pattern could reflect something deeper about the nature of planetary evolution and the rarity of truly habitable conditions. Perhaps Earth-like worlds are much less common than we hoped, existing only under very specific circumstances that are rarely replicated elsewhere. The abundance of sub-Neptune planets in exoplanet surveys might actually be telling us that most worlds follow evolutionary paths that lead away from habitability rather than toward it. The psychological impact of these realizations extends far beyond the scientific community. For decades, popular culture has been filled with optimistic visions of a galaxy teeming with life, where habitable worlds are common and contact with alien civilizations is inevitable. The story of K218b suggests that this optimism might be misplaced, that we might be alone in a universe filled with worlds that seem promising but are actually barren. This possibility forces us to confront profound questions about our place in the cosmos and our responsibilities as potentially the only intelligent life in our cosmic neighborhood. If truly habitable worlds are rare, then Earth becomes not just our home, but perhaps the only refuge for consciousness and creativity in our region of the galaxy. The implications for how we treat our planet and each other become correspondingly more significant. Yet there's also something inspiring about the K218b controversy, even if the planet turns out to be uninhabitable. The scientific debate surrounding this distant world represents humanity at its best, using our most advanced technologies and sophisticated theories to probe the deepest questions about existence and our place in the universe. Even if we're wrong about K218b's habitability, the process of investigating this question is expanding our understanding of planetary science and pushing the boundaries of what's technologically possible. The story also highlights the remarkable fact that we can detect and analyze the atmospheric chemistry of worlds more than 100 light-years away. Just a few decades ago, exoplanets were purely theoretical objects. Today we can determine the molecular composition of their atmospheres and debate whether they might harbor life. This represents one of the greatest achievements in the history of science, regardless of what we ultimately conclude about specific worlds like K218b. The controversy has also sparked important conversations about how science communicates with the public about potentially revolutionary discoveries. The initial excitement surrounding K218b's potential habitability generated global headlines and captured public imagination in ways that more cautious scientific language might not have achieved. But the subsequent debates and revisions have also led to disappointment and confusion about what scientists actually know versus what they hope to discover. This communication challenge will only become more pressing as our exoplanet detection capabilities continue to improve. We're entering an era where potentially habitable worlds will be discovered regularly, each one generating its own cycle of excitement, analysis, and possible disappointment. Learning how to manage public expectations while maintaining scientific rigor will be crucial for preserving public support for these expensive and technically challenging research programs. The K218b story also illustrates how scientific understanding evolves through the messy, contentious process of debate and revision. The planet's transformation from potentially habitable super-Earth to possibly hostile mini-Neptune hasn't happened through any single dramatic discovery, but through the gradual accumulation of evidence and the refinement of theoretical models. This process can be frustrating for those who want clear answers, but it represents how science actually works when confronting questions at the limits of current knowledge and technology. As we stand back and survey the full arc of K218b's story, from initial discovery to current controversy, we see a microcosm of humanity's broader relationship with the cosmos. We are a species that evolved on a single, remarkable world, trying to understand the nature of countless other worlds scattered across impossible distances. We bring to this task all of our hopes, fears, biases, and limitations, along with our remarkable capacities for creativity, analysis, and technological innovation. K218b may not be the second Earth we hope to find, but it has taught us invaluable lessons about the complexity of planetary environments and the challenges of searching for life beyond our solar system. Whether this distant world ultimately proves to be a hostile mini-Neptune, an exotic Hycean planet, or something else entirely, it has already earned its place in the history of astronomical discovery as the world that forced us to reconsider our assumptions about habitability and confront the possibility that truly Earth-like planets might be far rarer than we dared to imagine. The implications of K218b's story extend far beyond this single world, reaching into the very heart of how we understand planetary formation and the distribution of habitable environments throughout the galaxy. Recent surveys by the Kepler Space Telescope and other planet-hunting missions have revealed that sub-Neptune planets, like K218b, are actually among the most common types of worlds in our galaxy. These planets, ranging from about 1.7 to 4 times Earth's radius, represent a category of world that simply doesn't exist in our own solar system, creating a cosmic blind spot in our understanding of planetary evolution. This abundance of sub-Neptunes initially seemed like wonderful news for the search for habitable worlds. If most planets in the galaxy fell into this size range, and if some of them could maintain temperate conditions suitable for life, then habitable worlds might be far more common than anyone had dared hope. The Hycean world hypothesis suggested that these hydrogen-wrapped ocean planets could remain habitable even at greater distances from their stars than traditional rocky planets, potentially expanding the habitable zone around every star in the galaxy. But the mounting evidence against K218b's habitability suggests a far more sobering possibility. What if the very abundance of sub-Neptune planets in our galaxy actually represents a cosmic disappointment rather than a promise? What if these worlds, despite their prevalence and initial appeal, are fundamentally unsuitable for life as we know it? The implications would be staggering for our estimates of how common habitable worlds might be throughout the cosmos. Consider the mathematics of this possibility. Current surveys suggest that roughly 30 to 50% of all stars host sub-Neptune planets within what we traditionally consider habitable zones. If these worlds are actually hostile to life, then nearly half of all potentially habitable real estate in the galaxy might be nothing more than a cosmic mirage. Instead of expanding our catalogue of potentially life-bearing worlds, the study of planets like K218b might be systematically eliminating them from consideration. This realization has profound implications for one of the most famous questions in all of science: Enrico Fermi's paradox. If the universe should be teeming with life, Fermi asked his colleagues over lunch in 1950, then where is everybody? The absence of detectable alien civilizations has puzzled scientists for decades, leading to various theories about why advanced life might be rare or difficult to detect. The K218b story suggests a new and troubling answer to Fermi's question. Perhaps life isn't rare because intelligence is difficult to evolve, or because civilizations inevitably destroy themselves, or because advanced species choose to remain hidden. Perhaps life is rare because truly habitable planets are far less common than we've assumed. The galaxy might be filled with worlds that seem potentially habitable from a distance, but turn out to be utterly hostile when examined closely. This possibility forces us to reconsider our entire approach to the search for extraterrestrial life. The traditional strategy has been to cast a wide net, looking for any planets that might conceivably host liquid water, and then narrowing down the candidates through detailed study. But if most apparently habitable worlds are actually uninhabitable, then this approach might be fundamentally flawed. Instead, we might need to focus our limited resources on the smaller subset of planets that are most likely to be genuinely Earth-like. This means prioritizing rocky planets with thin atmospheres orbiting Sun-like stars, even though such worlds are much harder to detect and study with current technology. The irony is striking. The planets that are easiest to observe and analyze might be the least likely to actually harbor life. The debate over K218b has also highlighted the crucial importance of understanding planetary atmospheres in unprecedented detail. The difference between a habitable world and a hostile one might come down to subtle variations in atmospheric composition, pressure, and temperature that can only be detected through the most sophisticated spectroscopic analysis. This level of detail requires not just advanced technology, but also theoretical frameworks that can accurately model atmospheric behavior under conditions that don't exist anywhere in our solar system. Current atmospheric models for sub-Neptune planets are still in their infancy, largely because we have no local examples to study. The physics of hydrogen-rich atmospheres interacting with potential rocky cores and liquid water layers involves complex thermodynamic processes that push the boundaries of our current understanding. We're essentially trying to predict the behavior of entirely alien atmospheric systems, using theories developed to understand much simpler terrestrial environments. This theoretical gap has allowed for the kind of optimistic speculation that initially surrounded K218b. When our models are uncertain, there's room for hope that exotic atmospheric configurations might create habitable conditions in unexpected ways. But as our understanding improves, that wiggle room for optimism is steadily shrinking. The more we learn about the physics of sub-Neptune atmospheres, the more hostile these environments appear to become. The technological challenges facing future observations of K218b and similar worlds are equally daunting. Even the James Webb Space Telescope, the most powerful space-based observatory ever built, struggles to definitively characterize the atmospheric composition of distant exoplanets. The signals astronomers are trying to detect represent incredibly subtle changes in starlight that has traveled across dozens or hundreds of light-years of space, carrying information about atmospheric molecules that might exist in trace quantities. Future observations of K218b will need to address several key questions that remain unresolved. First, can the claimed detections of exotic molecules like dimethyl sulfide be confirmed through independent observations? Second, what does the overall atmospheric composition tell us about the planet's interior structure and thermal evolution? Third, are there any definitive signatures that could distinguish between a hydrogen-rich mini-Neptune and a Hycean ocean world? These questions will require not just additional observing time with Webb, but potentially entirely new observational strategies. Some researchers have proposed looking for temporal variations in K218b's atmospheric composition that might indicate active geological or biological processes. Others suggest searching for isotopic ratios that could reveal the planet's formation history and current thermal state. The proposed Habitable Worlds Observatory represents our best hope for definitively resolving questions about planets like K218b. This next-generation space telescope currently in the early planning stages, would be specifically designed to study Earth-sized planets in detail, with the sensitivity and stability needed to detect genuine biosignatures if they exist. But even this revolutionary instrument won't be operational until the 2040s, leaving us with decades of uncertainty about the true nature of worlds, like K218b. In the meantime, ground-based telescopes are pushing the boundaries of what's possible from Earth's surface. The upcoming Extremely Large Telescope, with its 39-meter primary mirror, will have the resolution to study exoplanet atmospheres in unprecedented detail. Advanced adaptive optics systems will allow these ground-based instruments to achieve image quality that rivals space-based telescopes, at least for certain types of observations. But perhaps the most important developments will come not from new hardware, but from advances in data analysis and theoretical modeling. Machine learning algorithms are beginning to play crucial roles in extracting subtle signals from noisy observational data. Sophisticated atmospheric models are incorporating increasingly detailed physics of exotic planetary environments. These computational advances might reveal insights about K218b and similar worlds that pure observational data cannot provide. The broader implications of the K218b controversy extend into the realm of astrobiology and our search for life beyond Earth. The planet's story illustrates how easy it is to mistake exotic chemistry for biological activity, especially when we're dealing with environments so different from Earth that our intuitions completely fail us. This challenge will only become more pressing as we discover and study more potentially habitable worlds. The false positive problem in biosignature detection is particularly acute because life as we know it tends to produce molecules that can also form through non-biological processes under the right conditions. Oxygen can be produced by photochemical reactions in planetary atmospheres. Methane can emerge from geological processes in planetary interiors. Even complex organic molecules can form through purely chemical reactions in space environments. Distinguishing between biological and non-biological sources for these molecules requires understanding the broader environmental context in which they exist. On Earth, we can identify biological signatures not just because certain molecules are present, but because they exist in combinations and concentrations that would be difficult to maintain through purely chemical processes. Extending this approach to exoplanets requires detailed knowledge of atmospheric chemistry, planetary geology, and evolutionary history that we may never possess for distant worlds. The K218b story also raises profound questions about the diversity of potentially habitable environments in the universe. Our search for life has been guided primarily by the principle of following the water, looking for worlds where liquid H2O might exist on planetary surfaces. But what if this approach is too narrow? What if life can adapt to environments so exotic that our Earth-based concepts of habitability become irrelevant? Some researchers have begun exploring the theoretical possibility that life might exist in high-pressure hydrogen atmospheres, like those potentially found on K218b. Such organisms would need to operate through chemical pathways that don't exist on Earth, perhaps using the abundant hydrogen as an energy source or building complex molecules from the exotic chemistry of high-pressure environments. This speculation pushes astrobiology into truly uncharted territory. We would be looking for life forms so fundamentally different from terrestrial biology that we might not recognize them as living organisms even if we encountered them directly. Their metabolism, reproduction, and evolutionary processes might operate according to principles that have no analogue in Earth's biosphere. The possibility of such exotic life raises fascinating questions about our detection methods and search strategies. If alien organisms use hydrogen chemistry rather than water-based biochemistry, they might produce atmospheric signatures that current biosignature research hasn't even considered. We could be surrounded by thriving alien biospheres that remain completely invisible to our current search techniques. But this speculation also highlights the fundamental challenge facing astrobiology. How do you search for something when you don't know what it looks like? Our entire framework for understanding life is based on a single example: the biosphere that evolved on Earth. Extrapolating from this lone data point to the full range of possibilities for biological organization throughout the universe is an exercise fraught with uncertainty and potential bias. The psychological dimensions of the K218b controversy reveal something profound about humanity's relationship with the cosmos and our deep need to find meaning and connection in the universe. The initial excitement about this distant world's potential habitability reflected more than just scientific curiosity. It represented hope that we might not be alone in the vast darkness of space. This hope can be both inspiring and dangerous. It drives us to push the boundaries of technology and theory, to ask profound questions about existence and meaning, to invest enormous resources in exploring the cosmos. But it can also lead us to see what we want to see rather than what's actually there, to interpret ambiguous data optimistically, and to embrace conclusions that aren't fully supported by evidence. The scientific method is designed to guard against these biases through peer review, reproducibility requirements, and standards of evidence that demand extraordinary proof for extraordinary claims. But even these safeguards aren't perfect, especially when we're dealing with phenomena at the very limits of our technological and theoretical capabilities. The K218b story illustrates both the power and the limitations of the scientific process. The initial optimistic interpretations of the planet's atmospheric data were based on legitimate scientific analysis using the best available methods and theories. The subsequent skeptical reassessments emerged through the same scientific process, as researchers applied different analytical techniques and considered alternative explanations. This ongoing debate isn't a failure of science, it's science working exactly as it should when confronted with complex, ambiguous data about phenomena we don't fully understand. The controversy is pushing astronomers to develop better observational techniques, more sophisticated theoretical models, and clearer criteria for evaluating potentially revolutionary claims. But the public reception of this scientific debate has been more problematic. The initial headlines proclaiming K218b as a potentially habitable super-Earth generated enormous excitement and captured global imagination. The subsequent doubts and revisions have led to confusion and disappointment, with some observers concluding that scientists don't know what they're talking about, or that the search for extraterrestrial life is futile. This communication challenge reflects a deeper tension between the messy, uncertain process of scientific discovery and the public's desire for clear, definitive answers about profound questions. Science advances through tentative hypotheses, careful testing, and gradual refinement of understanding, but public discourse often demands immediate certainty about complex issues that may not have simple answers. The K218b controversy has also sparked important discussions about how we should prioritize our limited resources for exoplanet research. Studying distant worlds requires some of the most expensive and technologically sophisticated instruments ever built. The James Webb Space Telescope cost over $10 billion to develop and deploy. Future missions like the Habitable Worlds Observatory will require similar investments of public funds. Given these enormous costs, how should we decide which planets deserve detailed study? Should we focus on the worlds that are easiest to observe, even if they might be less likely to be habitable? Should we prioritize smaller, more Earth-like planets that are harder to study but potentially more promising? Should we cast a wide net and study many planets superficially, or focus intensively on a few carefully selected targets? The K218b story suggests that we might need to reconsider our current approach. The planet's size and atmospheric properties made it an attractive target for detailed study, but those same characteristics might actually make it unsuitable for life. Future surveys might need to be more selective about which worlds receive intensive follow-up observations. This selectivity will require developing better criteria for predicting which planets are most likely to be genuinely habitable. Current models suggest that truly Earth-like worlds should be rocky planets with thin atmospheres orbiting stable stars. At distances where liquid water can exist on their surfaces. Such worlds might be rare and difficult to study, but they might represent our best hope for finding genuine biosignatures. The search for such worlds will require new technologies and techniques that can detect and characterize smaller planets with greater precision than current instruments allow. This technological development will take decades and require sustained international cooperation and investment. The scientific payoff could be extraordinary, but the path forward is long and uncertain. As we look toward the future of exoplanet science and astrobiology, the story of K218b serves as both a cautionary tale and an inspiration. The planet has taught us that the universe is far more complex and surprising than our Earth-based intuitions suggest. Worlds that seem potentially habitable from a distance might be utterly alien when examined closely. The search for life requires not just advanced technology, but also intellectual humility and willingness to accept that our hopes and expectations might be wrong. Yet there's something profoundly inspiring about humanity's ability to study worlds separated from us by more than 100 light-years of empty space. The fact that we can detect and analyze the atmospheric chemistry of such distant planets represents one of the greatest achievements in the history of science. Even if K218b turns out to be uninhabitable, the process of investigating this question has expanded our understanding of planetary science and pushed the boundaries of what's technologically possible. The controversy has also demonstrated the international, collaborative nature of modern astronomical research. Scientists from dozens of countries have contributed observations, theoretical insights, and analytical techniques to understanding this distant world. The debates about K218b's habitability have played out in conferences, journals, and observatories around the globe, representing humanity's collective effort to understand our place in the cosmos. This global scientific collaboration offers hope that we can overcome the challenges facing exoplanet research and astrobiology. The questions we're trying to answer: are we alone? How common is life in the universe? What conditions are necessary for biology to emerge? Transcend national boundaries and cultural differences. They represent fundamental human curiosity about existence and meaning that unites us across all divisions. The K218b story also highlights the remarkable progress that's been made in exoplanet science over just the past few decades. The first confirmed exoplanets were discovered only in the 1990s. Today, we know of thousands of worlds orbiting distant stars, and we can analyze their atmospheric chemistry in detail. This rapid progress suggests that even more revolutionary discoveries might be just around the corner. Future surveys will undoubtedly discover planets that are even more intriguing and controversial than K218b. Some of these worlds might turn out to be genuinely habitable, with atmospheric compositions that provide compelling evidence for biological activity. Others might reveal forms of planetary evolution and atmospheric chemistry that we've never imagined. Each new discovery will expand our understanding of what's possible in the universe and our place within it. The technological horizon offers reasons for both optimism and caution. The instruments being developed for the next generation of exoplanet research will be far more capable than anything currently available. The Habitable Worlds Observatory will be able to study Earth-sized planets in unprecedented detail. Ground-based telescopes will achieve resolutions that rival space-based instruments. Advanced computational techniques will extract more information from observational data than ever before. But these same technological advances will also reveal new complexities and challenges that we haven't yet anticipated. Each improvement in our observational capabilities tends to reveal that the universe is more complicated and surprising than we expected. The simple picture of habitable zones and Earth-like planets that guided early exoplanet research has given way to a far more nuanced understanding of planetary diversity and atmospheric complexity. The K218b controversy represents a crucial step in this evolution of understanding. The planet has forced us to confront the limitations of our current theories and methods, while pointing toward more sophisticated approaches to studying distant worlds. Whether K218b ultimately proves to be a hostile mini-Neptune, an exotic Hycean world, or something else entirely, it has already earned its place in the history of astronomical discovery. As we continue to unravel the mysteries of this distant world, we're also writing the next chapter in humanity's greatest adventure, the search for our place in the cosmic order. K218. B may not be the second Earth we hope to find, but it has taught us invaluable lessons about the complexity of planetary environments and the challenges of searching for life beyond our solar system. The story reminds us that the universe is under no obligation to conform to our expectations or fulfill our desires for cosmic companionship. But it also demonstrates our remarkable ability to probe the deepest mysteries of existence using the tools of science and reason. Whether we ultimately find life on K218b or elsewhere in the galaxy, the search itself represents one of the most profound expressions of human curiosity and ingenuity. In the end, K218b's greatest contribution to science might not be as a potentially habitable world, but as a teacher that has shown us how much we still have to learn about planets, life, and our place in the vast cosmos that surrounds us. The implications ripple outward, like waves in a cosmic pond, touching every aspect of how we understand our place in the universe. When we step back and examine the full scope of what K218b represents, we're confronting something far more profound than the habitability of a single, distant world. We're grappling with the possibility that our entire framework for understanding life in the cosmos might be fundamentally flawed. Think about what this means for the famous Drake equation, the elegant formula astronomers use to estimate how many communicating civilizations might exist in our galaxy. One of the key variables in that equation is the fraction of planets that could support life. For decades, scientists have been increasingly optimistic about this number, especially as we've discovered that rocky planets in habitable zones appear to be relatively common throughout the galaxy. But K218b's story suggests we might have been counting our cosmic chickens before they hatched. If sub-Neptune planets, which make up a huge percentage of all known exoplanets, are actually hostile to life rather than potentially habitable, then we need to dramatically revise our estimates downward. The galaxy might be far lonelier than we dared imagine. This realization forces us to confront some deeply uncomfortable possibilities about the nature of planetary evolution. Perhaps there's something special about our solar system's architecture that we've been taking for granted. The clear separation between rocky inner planets and gas giants in the outer system might not be the cosmic norm we assumed it was. Instead, it might represent a relatively rare configuration that's particularly conducive to the formation of truly habitable worlds. Consider what makes Earth genuinely special in this context. Our planet sits at just the right distance from a stable, long-lived star. It has exactly the right mass to maintain a thin atmosphere without becoming dominated by hydrogen and helium. Its magnetic field protects the surface from deadly radiation. Its large moon stabilizes the axial tilt that gives us stable seasons. The list of apparently necessary conditions keeps growing longer as we study more exoplanets and discover how many ways planetary evolution can go wrong. The psychological impact of these revelations extends far beyond the scientific community. For generations, science fiction has painted pictures of a galaxy teeming with habitable worlds where space travelers could expect to find Earth-like environments orbiting most stars. The optimism of Star Trek's infinite diversity in infinite combinations might need to give way to a more sober recognition that truly habitable worlds are precious rarities in a mostly hostile cosmos. But perhaps the most troubling aspect of K218b's story is what it reveals about our own scientific biases and limitations. The planet became famous precisely because it was easier to study than smaller, more Earth-like worlds. Its large size allowed telescopes to detect atmospheric signatures that would be impossible to observe on genuinely terrestrial planets. We were drawn to K218b not because it was the most likely to be habitable, but because it was the most convenient to investigate. This selection bias might be systematically leading us toward worlds that appear promising but are actually hostile. The planets we can study in detail with current technology might be precisely the ones that are least likely to support life. It's like trying to understand human nature by only interviewing people who are tall enough to reach the top shelf at the library. You might get interesting data, but it won't tell you much about humanity as a whole. The irony becomes even sharper when we consider what genuinely Earth-like planets would look like to our telescopes. Small rocky worlds with thin atmospheres orbiting sun-like stars would be incredibly difficult to detect and analyze with current technology. Their atmospheric signatures would be so subtle that they might remain completely invisible to instruments like the James Webb Space Telescope. We could be surrounded by perfect twins of Earth and never know it, because they're too similar to our home world to show up in our surveys. This technological limitation has profound implications for how we prioritize our search for extraterrestrial life. Should we continue studying worlds like K218b that are easy to observe, but probably hostile? Or should we focus our limited resources on developing the next generation of instruments that could detect and characterize truly Earth-sized planets? The choice isn't just technical, it's philosophical, reflecting our fundamental assumptions about what kinds of worlds are worth investigating. The debate over Hycean worlds sits at the center of this dilemma. These hypothetical planets, with their hydrogen-rich atmospheres overlying vast liquid water oceans, represent either an exciting expansion of habitable possibilities or a dangerous distraction from genuinely promising worlds. K218b was supposed to be our first confirmed example of this new category of potentially life-bearing planets. Its controversial nature now casts doubt on whether Hycean worlds can exist at all under real physical conditions. Recent theoretical work has been particularly damaging to the Hycean hypothesis. Sophisticated climate models suggest that most sub-Neptune planets would experience runaway greenhouse effects that would boil away any surface water long before stable ocean conditions could develop. The hydrogen atmospheres that were supposed to create protective blankets might actually function as cosmic pressure cookers, trapping heat so effectively that even the most resilient forms of life would be instantly sterilized. But here's where the story takes a fascinating turn toward even more exotic possibilities. Some researchers have begun seriously exploring whether life itself might be far more adaptable than our Earth-based experience suggests. What if organisms could evolve to thrive in high-pressure hydrogen atmospheres? What if the crushing conditions we consider lethal could actually provide energy sources for forms of biochemistry we've never imagined? This speculation pushes astrobiology into truly uncharted territory. We're talking about life forms that might use completely different chemical pathways than anything that evolved on Earth. Organisms that could harness the immense pressures and temperatures of hydrogen-rich atmospheres to drive metabolic processes that have no terrestrial analogue. Such life would be so fundamentally alien that we might not recognize it as biology, even if we encountered it directly. The possibility raises profound questions about our search methodologies and detection strategies. Current biosignature research focuses almost exclusively on molecules and processes familiar from Earth's biosphere. Oxygen produced by photosynthesis, methane generated by microbial metabolism, complex organic compounds that form under temperate conditions. But if alien life operates through hydrogen chemistry at extreme pressures and temperatures, these traditional signatures would be completely irrelevant. Imagine trying to detect a thriving civilization of hydrogen-based organisms on a world like K218b. Their metabolic processes might produce molecular combinations we've never seen, operating at energy levels that would instantly destroy Earth-based biochemistry. Their atmospheric signatures might look like pure chemistry to our instruments, indistinguishable from the exotic reactions occurring in crushing superheated gas envelopes. This possibility transforms our understanding of the false positive problem in biosignature detection. We've been worried about mistaking non-biological chemistry for signs of life. But what if we're actually making the opposite error? What if we're dismissing genuine biological activity because it operates according to principles so different from terrestrial life that we don't recognize it as living processes at all? The implications extend far broader search for extraterrestrial intelligence. If life can, beyond K218, be to our adapt to environments as extreme as those potentially found on sub-Neptune planets, then the galaxy might be teeming with forms of biology that remain completely invisible to our current detection methods. We could be surrounded by thriving alien civilizations that operate according to physics and chemistry so exotic that they exist in a parallel universe. Of possibility we haven't even begun to explore. But this speculation also highlights the fundamental challenge facing astrobiology in the 21st century. How do you search for life when you don't know what it looks like? Our entire theoretical framework is based on a single example: the biosphere that evolved on Earth over 4 billion years. Extrapolating from this lone data point to the full range of possibilities for biological organization throughout the universe is an exercise fraught with uncertainty and potential blindness. The technological horizon offers both promise and additional complexity. The James Webb Space Telescope represents the current pinnacle of exoplanet characterization capability, but even this revolutionary instrument struggles with the subtleties of atmospheric interpretation that the K218b controversy has revealed. Future missions like the proposed Habitable Worlds Observatory will be specifically designed to study Earth-sized planets in unprecedented detail, but these instruments won't be operational until the 2040s. In the meantime, ground-based telescopes are pushing the boundaries of what's possible from Earth's surface. The upcoming Extremely Large Telescope, with its 39-meter primary mirror, will have the resolution to study exoplanet atmospheres with unprecedented precision. Advanced adaptive optics systems are beginning to achieve image quality that rivals space-based instruments for certain types of observations. But perhaps the most important developments will come from advances in data analysis and theoretical modeling rather than new hardware. Machine learning algorithms are revolutionizing how astronomers extract meaningful signals from noisy observational data. Sophisticated atmospheric models are incorporating increasingly detailed physics of exotic planetary environments that have no solar system analogues. These computational advances might reveal insights about K218b and similar worlds that pure observational data cannot provide. By running thousands of simulations of different atmospheric configurations and comparing them to actual telescope observations, researchers might be able to distinguish between competing theories about the planet's true nature. The question is whether these models are sophisticated enough to capture the full complexity of atmospheric behavior under conditions we've never directly studied. The broader implications for humanity's cosmic perspective are equally profound. The story of K218b represents our species coming to terms with the vast complexity and potential hostility of planetary environments throughout the galaxy. We are children of a remarkably stable and temperate world, trying to understand cosmic siblings that might be utterly alien in their fundamental nature. This humbling recognition might actually be healthy for our long-term development as a spacefaring civilization. If truly habitable worlds are rare and precious, then Earth becomes not just our home, but potentially the only refuge for consciousness and creativity in our cosmic neighborhood. The implications for how we treat our planet and each other become correspondingly more significant. The environmental and social challenges facing Earth take on new meaning when viewed against the backdrop of cosmic rarity. Climate change isn't just a threat to human civilization, it's potentially endangering one of the universe's most precious and irreplaceable treasures. The conflicts and divisions that plague human society become not just tragic wastes of potential, but cosmic squandering of perhaps the only intelligence in our region of the galaxy. Yet there's also something deeply inspiring about our species' determination to understand these distant worlds, despite the enormous technical and theoretical challenges involved. The fact that we can detect and debate the atmospheric chemistry of planets more than 100 light-years away represents one of the greatest achievements in the history of science. Even if K218b turns out to be completely hostile to life, the process of investigating this question has expanded human knowledge and capability in remarkable ways. The international collaboration surrounding K218b research also offers hope for humanity's future development. Scientists from dozens of countries have contributed observations, theoretical insights, and analytical techniques to understanding this distant world. The debates about the planet's habitability have transcended national boundaries and cultural differences, representing our species' collective effort to understand our place in the cosmos. This global scientific enterprise suggests that we might be capable of the kind of long-term thinking and cooperation that will be necessary for becoming a truly cosmic civilization. The questions we're trying to answer through exoplanet research: are we alone? How common is life in the universe? What conditions are necessary for biology to emerge? Represent fundamental human curiosity that unites us across all divisions. The communication challenges surrounding K218b have also provided valuable lessons about how science interfaces with public understanding and expectation. The initial excitement about the planet's potential habitability generated global headlines and captured imaginations in ways that more cautious scientific language might not have achieved. But the subsequent debates and revisions have led to confusion and disappointment among those who expected definitive answers about profound questions. This pattern reflects a deeper tension between the messy, uncertain process of scientific discovery and the public's desire for clear conclusions about complex issues. Science advances through tentative hypotheses, careful testing, and gradual refinement of understanding. But public discourse often demands immediate certainty about questions that may not have simple answers, especially when those questions touch on our deepest hopes and fears about our place in the universe. Learning to navigate this communication challenge will become increasingly important as our exoplanet detection capabilities continue to improve. We're entering an era where potentially habitable worlds will be discovered regularly, each generating its own cycle of excitement, analysis, and possible disappointment. Managing public expectations while maintaining scientific rigor will be crucial for preserving support for these expensive and technically demanding research programs. The economic dimensions of exoplanet research also deserve consideration. Studying distant worlds requires some of the most expensive and technologically sophisticated instruments ever built. The James Webb Space Telescope cost over $10 billion to develop and deploy. Future missions will require similar investments of public resources at a time when many pressing challenges demand attention here on Earth. Justifying these enormous expenditures requires making the case that understanding our cosmic context has value beyond pure scientific curiosity. The search for extraterrestrial life touches on fundamental questions about the nature of existence, the possibility of cosmic companionship, and humanity's long-term future as a spacefaring species. These might seem like abstract concerns, but they could prove crucial for our species' survival and development over cosmic timescales. The technological spillovers from exoplanet research also provide practical benefits that extend far beyond astronomy. The instruments and techniques developed for detecting and characterizing distant worlds often find applications in medical imaging, environmental monitoring, and advanced manufacturing. The computational methods used to analyze atmospheric data contribute to climate modeling and weather prediction. The international collaborations necessary for major space missions create relationships and capabilities that benefit many areas of human endeavor. But perhaps the most important justification for continued exoplanet research lies in what it teaches us about planetary processes and the conditions necessary for habitability. Even if we never find definitive evidence for extraterrestrial life, understanding how planetary atmospheres evolve and what factors determine habitability has direct relevance for managing our own planet's environmental challenges. The study of Venus's runaway greenhouse effect has informed our understanding of climate change on Earth. Research into Mars's atmospheric evolution has revealed how planets can lose their habitability over geological timescales. The investigation of exoplanet atmospheres is expanding this comparative planetology approach to include worlds with no solar system analogues, providing new insights into the full range of possible planetary environments. K218b's story fits perfectly into this broader framework of comparative planetary science. Whether the planet turns out to be a hostile mini-Neptune, an exotic Hycean world, or something else entirely, studying its atmospheric properties is expanding our understanding of how planetary environments can evolve under conditions very different from those in our own solar system. This knowledge has practical applications for long-term human space exploration and colonization efforts. As our species eventually ventures beyond Earth, we'll need to understand and adapt to planetary environments that might be radically different from our home world. The atmospheric physics and chemistry we're learning from studying exoplanets, like K218b, could prove crucial for developing the technologies and strategies necessary for surviving and thriving on alien worlds. The psychological and philosophical dimensions of exoplanet research deserve equal attention. The search for other worlds represents one of humanity's most profound expressions of curiosity and wonder about the cosmos. It reflects our deep need to understand our place in the universe and our longing for cosmic companionship that transcends the isolation of our single, small planet. This drive for cosmic understanding appears to be a fundamental aspect of human nature, emerging independently in cultures throughout history. Ancient astronomers mapped the movements of celestial bodies, medieval scholars debated the plurality of worlds, and modern scientists have made the search for exoplanets one of the most active and exciting areas of contemporary research. The consistency of this curiosity across time and culture suggests that the search for other worlds touches something essential about what it means to be human. The potential discovery of life beyond Earth would represent a watershed moment in human history, fundamentally altering our understanding of biology, philosophy, and our place in the cosmic order. But even the search itself, regardless of what we ultimately discover, is transforming how we see ourselves and our relationship to the universe around us. K218b embodies both the promise and the peril of this cosmic quest. The planet captured global attention because it seemed to offer everything we hope to find in an alien world: the right size, the right location, the right atmospheric chemistry to potentially harbour life. The subsequent debates and doubts have revealed how much we still don't understand about planetary environments and the conditions necessary for biology to emerge and thrive. But this uncertainty isn't a failure of science or a reason to abandon the search. It's a reminder that the universe is far more complex and surprising than our Earth-based intuitions suggest. Every world we study teaches us something new about the incredible diversity of planetary environments that exist throughout the galaxy. Each discovery expands our understanding of what's possible in the cosmic laboratory of planetary formation and evolution. The story of K218b also illustrates the self-correcting nature of scientific inquiry. Initial optimistic interpretations of the planet's atmospheric data were based on legitimate analysis using the best available methods and theories. The subsequent skeptical reassessments emerged through the same scientific process as researchers applied different analytical techniques and considered alternative explanations for the observed phenomena. This ongoing debate represents science working exactly as it should when confronted with complex, ambiguous data about phenomena at the limits of our understanding. The controversy is driving improvements in observational techniques, theoretical models, and analytical methods that will benefit all areas of exoplanet research. Even if K218b turns out to be uninhabitable, the process of investigating its properties is advancing human knowledge and capability in measurable ways. The international nature of this scientific enterprise also offers hope for humanity's ability to cooperate on challenges that transcend national boundaries. The researchers studying K218b represent dozens of countries and institutions, working together to understand a world that belongs to no nation but captures the imagination of our entire species. This collaboration across political and cultural divides suggests that we might be capable of the kind of global cooperation necessary for addressing other cosmic-scale challenges. As we look toward the future of exoplanet science and our search for life beyond Earth, K218b will likely be remembered as a crucial turning point in our understanding. The planet forced us to confront the limitations of our current theories and methods while pointing toward more sophisticated approaches to studying distant worlds. Whether it ultimately proves to be hostile or habitable, K218b has already earned its place in the history of astronomical discovery as the world that taught us how much we still have to learn. The coming decades will bring revolutionary new instruments and techniques that could definitively resolve the questions surrounding K218b and similar worlds. The Habitable Worlds Observatory will be able to study Earth-sized planets with unprecedented precision. Ground-based telescopes will achieve resolutions that rival space-based instruments. Advanced computational methods will extract more information from observational data than ever before possible. These technological advances will undoubtedly reveal new complexities and surprises that we haven't yet imagined. Each improvement in our observational capabilities tends to show that the universe is more complicated and diverse than we expected. The simple picture of habitable zones and Earth-like planets that guided early exoplanet research has already given way to a far more nuanced understanding of planetary diversity and atmospheric complexity. K218b represents a crucial step in this evolution of understanding. The planet has forced us to question our assumptions, refine our methods, and develop more sophisticated theoretical frameworks for understanding distant worlds. It has taught us that the search for life requires not just advanced technology, but also intellectual humility and willingness to accept that our hopes and expectations might be wrong. But perhaps most importantly, K218b has reminded us that we are participants in one of the greatest adventures in human history, the quest to understand our place in the cosmic order. Whether this distant world proves to be a second Earth or a cautionary tale about the rarity of habitable planets, it represents our species' determination to push beyond the boundaries of our home world and explore the infinite possibilities that await us among the stars. The universe may not be obligated to fulfill our desires for cosmic companionship, but it continues to surprise us with its complexity and beauty. K218b may not be the answer to our search for extraterrestrial life, but it has already provided something equally valuable: a deeper appreciation for the remarkable nature of our own planet and the extraordinary challenge of finding its siblings in the vast darkness of space. As we continue to unravel the mysteries of this distant world, we're also writing the next chapter in humanity's greatest story, our gradual awakening to the true nature of the cosmos and our place within it. The journey is far from over, and the most profound discoveries may still lie ahead, waiting to be revealed by the next generation of cosmic explorers who will carry forward the legacy of wonder and determination that K218b has come to represent. But the stakes of this cosmic deception might be even higher than anyone imagined. As we examine the broader implications of K218b's story, we begin to see patterns that suggest our entire approach to finding habitable worlds might be fundamentally misguided. The planet that was supposed to herald a new era of exoplanet discovery might instead be teaching us that the universe is a far lonelier place than we ever dared to contemplate. Consider the disturbing possibility that K218b represents not an exception, but the rule. The galaxy might be filled with worlds that tantalize us from afar with the promise of habitability, only to reveal themselves as hostile imposters when examined closely. These cosmic mirages could be systematically misleading our search for life, drawing our attention and resources toward planets that appear promising but are actually barren. The mathematics of this deception are sobering. Current surveys suggest that sub-Neptune planets like K218b make up roughly 30 to 50% of all worlds orbiting within what we traditionally call habitable zones. If these planets are systematically uninhabitable despite their promising appearances, then nearly half of all potentially life-bearing real estate in the galaxy might be nothing more than an elaborate cosmic joke. This possibility forces us to confront one of the most unsettling questions in modern astronomy. What if we're not just rare, but virtually alone? The silence we've encountered in our searches for extraterrestrial intelligence might not reflect the difficulty of interstellar communication or the tendency of civilizations to remain hidden. It might simply be telling us that worlds capable of supporting complex life are so uncommon that we represent one of the only experiments in consciousness currently operating in our cosmic neighborhood. The psychological implications are staggering. For decades, popular culture has painted pictures of a galaxy teeming with habitable worlds, where space explorers could expect to find Earth-like environments orbiting most stars. The optimistic vision of countless civilizations scattered across the cosmos might need to give way to a much more sober recognition that truly habitable planets are precious rarities in a mostly hostile universe. Yet even as K218b challenges our assumptions about habitability, it's also revealing possibilities for life that we never imagined. Some researchers have begun seriously exploring whether biology itself might be far more adaptable than our terrestrial experience suggests. What if life could evolve to thrive in the crushing hydrogen atmospheres that make planets like K218b seem so hostile to our Earth-based intuitions? This speculation pushes astrobiology into truly alien territory. We're talking about organisms that might use completely different chemical pathways than anything that evolved on our planet. Life forms that could harness the immense pressures and temperatures of hydrogen-rich environments to drive metabolic processes that have no earthly analogue. Such biology would be so fundamentally different from terrestrial life that we might not recognize it as living even if we encountered it directly. Picture microscopic organisms floating in K218b's dense atmosphere, using the abundant hydrogen as an energy source while building complex molecular structures from the exotic chemistry of high-pressure environments. These hypothetical life forms might thrive in conditions that would instantly sterilize any Earth-based biology, operating according to principles that push the boundaries of what we consider possible for living systems. The possibility transforms our understanding of the false positive problem in biosignature detection. We've been worried about mistaking non-biological chemistry for signs of life. But what if we're actually making the opposite error? What if we're dismissing genuine biological activity because it operates according to principles so different from terrestrial life that we don't recognize it as biology at all? Consider the implications for our current search strategies. The James Webb Space Telescope and other advanced instruments are specifically designed to look for molecular signatures familiar from Earth's biosphere: oxygen produced by photosynthesis, methane generated by familiar metabolic processes, water vapor indicating temperate surface conditions. But if alien life operates through hydrogen chemistry at extreme pressures and temperatures, these traditional biosignatures would be completely irrelevant. We could be surrounded by thriving alien civilizations that remain invisible to our detection methods, not because they're trying to hide, but because they exist in a parallel universe of biological possibility that we haven't learnt to perceive. The atmospheric signatures we dismiss as purely chemical might actually represent the metabolic processes of organisms so exotic that they exist beyond our current concepts of life and death. This possibility raises profound questions about the diversity of consciousness that might exist throughout the cosmos. If biology can adapt to environments as extreme as those potentially found on K218b, then intelligence might emerge in forms so alien that our attempts at interstellar communication become meaningless. We might be broadcasting radio signals into space while advanced civilizations communicate through quantum mechanical processes or manipulations of matter and energy that we can't even detect, let alone understand. The debate over K218b has also highlighted the crucial importance of technological humility as we push the boundaries of exoplanet science. The James Webb Space Telescope represents humanity's most advanced tool for studying distant worlds. Yet even this revolutionary instrument struggles with the subtleties of atmospheric interpretation that the K218b controversy has revealed. We're trying to understand planetary environments based on incredibly limited information, brief glimpses of starlight filtered through alien atmospheres that might operate according to physics we've barely begun to explore. Future missions promise even greater capabilities, but they also threaten to reveal new layers of complexity that could make our current debates seem simple by comparison. The proposed Habitable Worlds Observatory, scheduled for deployment in the 2040s, will be able to study Earth-sized planets with unprecedented precision. But what if this enhanced capability simply reveals that the universe is even more strange and diverse than our current instruments suggest? The ground-based telescopes currently under construction, like the extremely large telescope with its 39-meter primary mirror, will achieve resolutions that could revolutionize our understanding of exoplanet atmospheres. Advanced adaptive optics systems are beginning to provide image quality that rivals space-based instruments for certain types of observations. But each technological leap forward also expands the range of phenomena we need to understand and interpret. The computational revolution in astronomy is equally promising and challenging. Machine learning algorithms are beginning to extract meaningful signals from observational data that human analysts might miss entirely. Sophisticated atmospheric models can simulate planetary environments under conditions that have no solar system analogues. But these same tools also reveal how much we don't know about the fundamental physics and chemistry of exotic planetary environments. As we develop increasingly powerful methods for studying distant worlds, we're also discovering that each planet represents a unique experiment in physics and chemistry that might have no direct comparison anywhere else in the universe. K2-18b's atmospheric composition and structure might be unlike anything we'll ever encounter again, making it difficult to draw broader conclusions about habitability from studying any single world. This uniqueness paradox sits at the heart of exoplanet science. Each world we discover expands our understanding of what's possible in planetary formation and evolution. But the very diversity that makes these discoveries exciting also makes it difficult to develop general theories about which planets are most likely to support life. We might need to study hundreds or thousands of worlds before we can confidently predict which characteristics indicate genuine habitability. The timescales involved in this research are both inspiring and humbling. The light we're analysing from K2-18b began its journey toward Earth more than a century ago, long before humans had any idea that planets existed beyond our solar system. The molecules we're debating in the planet's atmosphere have been floating in that alien environment for millions or billions of years, carrying information about processes we're only beginning to understand. Yet our analysis of this ancient light represents one of the most sophisticated scientific endeavours in human history. We're using quantum mechanical principles to understand how specific molecules absorb infrared radiation, then applying complex statistical techniques to extract meaningful signals from data that contains more noise than signal. The entire enterprise pushes the boundaries of what's technologically and theoretically possible. The international collaboration surrounding K2-18b research offers a glimpse of humanity at its best. Scientists from dozens of countries have contributed observations, theoretical insights, and analytical techniques to understanding this distant world. The debates about the planet's habitability have transcended political boundaries and cultural differences, representing our species' collective effort to understand our place in the cosmos. This global scientific enterprise suggests that we might be capable of the kind of long-term thinking and cooperation that will be necessary for eventually reaching and studying these distant worlds directly. The questions we're trying to answer through exoplanet research represent fundamental human curiosity that unites us across all divisions. Whether we're alone in the universe, how common life might be throughout the cosmos, and what conditions are necessary for biology to emerge and thrive are concerns that speak to something essential about human nature. The economic dimensions of this research also deserve recognition. Studying worlds like K2-18b requires some of the most expensive and technologically sophisticated instruments ever built. The James Webb Space Telescope cost over $10 billion to develop and deploy. Future missions will require similar investments at a time when numerous pressing challenges demand attention here on Earth. But the potential returns extend far beyond pure scientific knowledge. The technologies developed for detecting and characterizing distant planets often find applications in medical imaging, environmental monitoring, and advanced manufacturing. The computational methods used to analyze atmospheric data contribute to climate modeling and weather prediction. The international collaborations necessary for major space missions create relationships and capabilities that benefit many areas of human endeavor. Perhaps most importantly, understanding planetary atmospheres and the conditions that determine habitability has direct relevance for managing our own planet's environmental challenges. The study of Venus's runaway greenhouse effect has informed our understanding of climate change on Earth. Research into Mars's atmospheric evolution reveals how planets can lose their habitability over geological timescales. The investigation of exotic atmospheres on worlds like K2-18b expands this comparative approach to include environments that have no solar system analogues. The philosophical implications of K2-18b's story resonate far beyond astronomy and planetary science. The planet represents humanity's attempt to understand its cosmic context through the tools of science and reason. Whether K218b ultimately proves habitable or hostile, the process of investigating this question demonstrates our species' remarkable capacity for curiosity and wonder about the universe around us. This drive to understand distant worlds appears to be a fundamental aspect of human nature, emerging independently across cultures and throughout history. Ancient astronomers mapped the movements of celestial bodies, medieval scholars debated the plurality of worlds, and modern scientists have made exoplanet research one of the most active and exciting areas of contemporary investigation. The consistency of this curiosity suggests that the search for other worlds touches something essential about what it means to be human. The potential discovery of life beyond Earth would represent a watershed moment in human history, fundamentally altering our understanding of biology, philosophy, and our place in the cosmic order. But even the search itself, regardless of what we ultimately discover, is transforming how we see ourselves and our relationship to the universe around us. K218b embodies both the promise and the complexity of this cosmic quest. The planet captured global attention because it seemed to offer everything we hoped to find: the right size, the right location, the right atmospheric chemistry to potentially harbour life. The subsequent debates and uncertainties have revealed how much we still don't understand about planetary environments and the conditions necessary for biology to emerge and thrive. But this uncertainty isn't a failure of science or a reason to abandon the search. It's a reminder that the universe is far more complex and surprising than our Earth-based experience suggests. Every world we study teaches us something new about the incredible diversity of planetary environments that exist throughout the galaxy. Each discovery expands our understanding of what's possible in the cosmic laboratory of planetary formation and evolution. The story also illustrates the self-correcting nature of scientific inquiry. Initial interpretations of K218b's atmospheric data were based on legitimate analysis using the best available methods and theories. The subsequent revisions and debates emerged through the same scientific process, as researchers applied different techniques and considered alternative explanations for the observed phenomena. This ongoing controversy represents science working exactly as it should when confronted with complex, ambiguous data about phenomena at the limits of our understanding. The debates are driving improvements in observational techniques, theoretical models, and analytical methods that will benefit all areas of exoplanet research. Even if K218b turns out to be completely uninhabitable, the process of investigating its properties is advancing human knowledge in measurable ways. As we look toward the future, K218b will likely be remembered as a crucial turning point in our understanding of exoplanets and habitability. The planet forced us to confront the limitations of our current approaches while pointing toward more sophisticated methods for studying distant worlds. Whether it proves to be a second Earth or a cautionary tale about the rarity of habitable planets, K218b has already earned its place in the history of astronomical discovery. The coming decades will bring revolutionary new instruments and techniques that could definitively resolve the questions surrounding this enigmatic world. But they will also undoubtedly reveal new complexities and surprises that we haven't yet imagined. Each advance in our capabilities tends to show that the universe is more diverse and challenging than we expected. K218b has taught us that the search for life requires not just advanced technology, but also intellectual humility and willingness to accept that our hopes and expectations might be wrong. The planet has reminded us that we are participants in the quest to understand our place in the greatest adventures in human history: cosmic order. Whether K218b ultimately proves to be a world of crushing hydrogen atmospheres or exotic ocean chemistry, it represents our species' determination to push beyond the boundaries of our home planet and explore the infinite possibilities that await us among the stars. The universe may not be obligated to fulfill our desires for cosmic companionship, but it continues to surprise us with its complexity and beauty. Perhaps the greatest lesson K218b offers isn't about this particular world, but about the nature of scientific discovery itself. The planet has shown us that even our most sophisticated instruments and theories are just the beginning of understanding cosmic phenomena that challenge every assumption we hold about planets, atmospheres, and life itself. As we continue unraveling the mysteries of this distant world, we're writing the next chapter in humanity's greatest story, our gradual awakening to the true nature of the cosmos and our place within it. The journey is far from over, and the most profound discoveries may still lie ahead, waiting to be revealed by future generations of cosmic explorers who will carry forward the legacy of wonder and determination that K218b has come to represent. In the end, K218b may not be the second Earth we hope to discover, but it has given us something equally valuable, a deeper appreciation for the remarkable nature of our own planet and the extraordinary challenge of finding its siblings in the vast darkness of space. The dark truth about K218b isn't that it's uninhabitable, but that it's taught us how much we still don't know about the cosmos we call home. And perhaps that's exactly the lesson we needed to learn. So here we are, at the end of our journey through the controversial cosmos of K218b. We've travelled from the initial euphoria of discovering what seemed like humanity's best hope for finding a second Earth, through the sobering realization that this distant world might be one of the most hostile environments imaginable, to the profound questions it raises about our entire approach to searching for life among the stars. The dark truth about K218b isn't just that it might be uninhabitable, it's that this single world has forced us to confront the possibility that our cosmic loneliness might be far more profound than we ever dared imagine. The galaxy could be filled with worlds that tantalize us from afar with promises of habitability, only to reveal themselves as elaborate mirages when we look closer. We might be living in a universe where truly Earth-like planets are so rare that we represent one of the only successful experiments in consciousness currently operating in our cosmic neighborhood. But perhaps that's not the end of the story. Perhaps K218b is teaching us that life itself might be far more creative and adaptable than our terrestrial experience suggests. Maybe somewhere in those crushing hydrogen atmospheres, forms of biology we can't even imagine are thriving according to principles that have no earthly analogue. We could be surrounded by alien civilizations that remain invisible to our detection methods, not because they're hiding, but because they exist in realms of possibility we haven't learned to perceive. What keeps me awake at night isn't whether K218b harbours life as we know it. It's the humbling recognition that we're cosmic children trying to understand a universe that might be stranger, more diverse, and more wonderful than our Earth-based intuitions could ever grasp. Every world we study reveals new complexities that challenge our assumptions and expand our sense of what's possible in the grand laboratory of planetary formation and evolution. K218b may not be our second Earth, but it's given us something equally precious, a reminder that we're participants in the greatest detective story ever told. The universe doesn't owe us cosmic companions, but it continues to surprise us with its complexity and beauty. And in that surprise, in that constant expansion of wonder and possibility, we find not disappointment, but inspiration. The search continues, and the most profound discoveries may still lie ahead, waiting to be revealed by instruments we haven't built yet and minds we haven't educated yet. Whether we're alone or surrounded by alien life forms beyond our wildest imagination, the journey of discovery itself represents the very best of what it means to be human. Until we meet again on another cosmic journey, keep looking up, keep questioning, and remember that every point of light in the night sky might be hiding secrets that could change everything we thought we knew about our place in this vast, mysterious, and endlessly fascinating universe.